Today we are going to look at interpreting the meaning of a derivative in context. We've done a little bit of this, but we're going to really focus in on looking at units and being able to explain what a derivative means in context of a problem today. So the derivative is the instantaneous rate of change of the dependent variable which is your y, with respect to its independent variable, which is typically your x coordinate. And if you think about our symbol that we've used some for our derivative, it's dy dx, so the rate of change of the y with respect to the x. It also should remind us of our slope formula, because we know the derivative gives us the slope of the function at that point, and that's change in y over change in x. So the unit for f prime of x, the derivative of f, is the unit for f divided by the unit for x. And here, whenever we say f, that's whatever the name of the function is, but it's going to be on your y-axis, and of course the x will come from your x-axis. So whenever you're doing units, when you're looking for a derivative, it is change in y over change in x. So you can take the units for the y-axis and divide it by the units for the x-axis, and that gives you the units for your derivative. So let's look at this in context of a problem. So they tell us for this problem the function c equals f of t gives the cost in dollars of running a piece of equipment for t hours. So in this particular case, this t right here, that's going to go on our x-axis. All right, so if we're thinking about a little graph here, the x-axis, that's going to be our t, and then we could either call our y-axis f, or I'm going to call it c right here, because c equals that f of t. And it tells us that this function gives us the cost in dollars. That's your y coordinate, so cost in dollars. And running an equipment for t hours. So this is time in hours. And so when we look at that here, when we're thinking about the units for f prime of t, it's going to be change in y over change in x. So this would be for the graph of the cost here. When we take that derivative, it's change in y over change in x. In this particular case, that is change in c over change in t, which is going to be the cost in dollars per hour. So dollars per hour would be our unit here. So the derivative tells you the rate of change in dollars per hour. The second part asks us about the units for f double prime of t. So when we're thinking about the second derivative here, the x-axis doesn't change. It's still time in hours. Here, the y-axis is now c prime, which we said is measured in dollars per hour. Right? That's what our answer for the last problem was. So if we're thinking about the slope of the graph of the derivative, it is change in y over change in x. On our y-axis, we've got our c prime. On our x-axis, we still have change in t. And so our units for our y-axis here are dollars per hour, and our units for the denominator is hours. Now you can leave it like this, just write dollars per hour. That is okay. Or if we put hours over 1, we could do dollars per hour times 1 over hours, because dividing fractions is easy as pie. We flip the second and multiply, and we would get dollars per hour squared. So these are equivalent to each other. You can write it either way for this answer. All right, let's look at the second one. The time t it takes to run a distance d is given by the equation t equals r of d, where t is measured in hours and d is measured in miles. And so this problem's a little backwards from the way we usually think of time and distance, because distance is on our x-axis here, and t for time, that's on our y-axis. So if we again think of making that little graph, we've got t here and d here. So our distance, which we're told is measured in miles, goes on the x-axis. Our time, which is measured in hours, goes on the y-axis. So if we're looking for the units of r prime of d, we're thinking change in y over change in x, because the derivative is a slope. Our y-axis here is hours, and our x-axis is mile. So our units are hours per mile. That sounds backwards because we're usually thinking about miles per hour, but rather this is the number of hours it takes you to run each mile. So it's a little bit backwards, but it's the answer to this problem. If they ask us for second derivative here, just like we did on the last problem, our x-axis would stay the same. We'd still have miles. That's our distance here. And then our y-axis is going to be the answer to A. That's hours per mile. So if we think about doing, that's our r prime right there. So if we think about doing this problem, we're going to have changing our y-axis over changing our x-axis. For this graph, for your graph of r prime, you got hours per mile, and then the units for the x-axis is miles. So again, you can write this as hours per mile per mile. That's one way you can write it, or you can do hours over miles times this is over 1 times 1 over miles, and you could also write it as hours per mile squared. So that would be another option there. For 3, we're given the length of a scarf is given by the function L equals S of t, where L, the length, is measured in centimeters, and time t is measured in minutes. What is the meaning of S prime of 7? So I like to think about what that graph looks like and what my units look like first, because I think the units help me answer this question for S prime of t. So t is the inside of the function, so it's your x-axis, and it tells us t is measured in minutes. So we've got minutes here on our x-axis, and then L is measured in centimeters, so it's length in centimeters. Okay, so when we're taking the derivative of L, or S here, you could call it either one, we're taking the derivative, we're finding the slope of our graph of L. So since our derivative is our slope of our graph of S, which would be some graph here, our units are going to be our change in y over change in x. On our y-axis, we've got centimeters. On our x-axis, we've got minutes. So whenever we talk about the answer to this question, our units should be in centimeters per minute. So S prime of 7 is measured in centimeters per minute. The other problems just had a variable there. They didn't have a number plugged in here. But since we have a 7 here, that tells me T is 7. T stands for time, so that's 7 minutes there. So we would say at 7 minutes, and then we're talking about the derivative, which is our rate of change of L. L is our length. So the length of the scarf is changing at a rate of S prime of 7 centimeters per minute. Now, I used S prime of 7 because I don't actually know the value of S prime of 7, so I can't plug a number in there. Also, I use this phrase right here, changing, so that is okay to say because we're talking about the rate of change here. If I knew if S prime was positive or negative, I could call it increasing or decreasing. If we have a positive rate of change, then our length would be increasing. If we have a negative rate of change, the length would be decreasing here, but I don't know that for sure, so I just said changing for this problem. Okay, for example 4, they actually give us an equation this time, and they tell us that h of t gives the height h of water in a swimming pool at time t. The height h is measured in feet at the time t is measured in hours since midnight. Find the instantaneous rate of change of the height of the water in the pool at 10 a.m. So if we think about our graph so we can think about units here, and this one's actually wanting us to figure out the answer here, and given these decimals here, I'm going to assume this will be calculator active, although we could do it by hand without too much trouble. We'll go ahead and pull up the calculator here for this one though. So if we think about our function here, t is on the inside, so t goes on the x-axis. It tells us t is measured in hours, so we got hours here on our x-axis. H of t, so h is our function here, and the height, h, is measured in feet. So we got feet here. So for our graph of h, whatever it looks like, we're looking at feet and hours. The question asks us for the instantaneous rate of change of the height of the water at 10 a.m. So what this problem is asking us for is the rate of change at the moment where we hit 10 a.m. So that is going to be our derivative at that point. So this question is asking us to find h prime of 10. So a lot of questions that you'll see, you won't necessarily have to explain what it means, but you'll have to understand what the question is asking for. So if we're finding h prime of 10, and this is calculator active, if I go to y equals and enter this 5.42 plus 2.3 times cosine of, I'm going to use an x minus 4 here. So I've entered my function. If I go back to my main screen, and clear it, you don't have to clear everything out, I just like to so it looks prettier. So we want to take the derivative and we want to plug in 10. So you got a couple options for this. If you just do the derivative, you're going to tell it derivative. You could either type this in, but I put it in y1, so I'm going to do y1 of x, comma, x. So if you do this, it will take the derivative. What happens there? oh, oops, I put it in Y2. So let's, I'm going to copy, I'm just going to cut this and paste it here and then clear it out. Or I could have just used the Y2. All right, let's try this again. All right, so this is my derivative. It's not that difficult to just do negative 2.3 sine of 10 minus 4, just to plug that in there. That's fine. Or an even quicker way is whenever you take the derivative, when you type that in, the derivative of y1 of x, comma, x, you can actually go, since you know you only care about plugging in 10, you can actually go ahead and plug in 10 here. So you'll do such that x equals 10, and then I'm going to hit the green button and then enter, so that I can get that number that way. So if you were asked to answer a question like this, and it was on Calculator Active, all you would have to say is that h prime of 10 equals 0.643, or you could keep more decimal places if you want, and you would need to put your units. So if I'm taking the derivative, and I've got feet on my y-axis, hours on my x-axis, this is going to be feet per hour. So at 10 a.m., the water in the pool is, amount of water in the pool is increasing at a rate of 0.643 feet per hour. And I know it's increasing because I have a positive rate of change here. All right. For our next problem, I've got this equation here, and it gives the weight of sand in a storage container after X days, where weight is measured in tons. And we're supposed to find S prime of 15 using correct units and explain the meaning. And then we're also supposed to talk about S double prime of 15. So this also would be Calculator Active. I'm going to go here to y equals, and I'm going to type in this equation. So 234 e to the negative 0.05 x plus 200, and we want to look to make sure that that looks correct. I believe it does. So if I go back to the main screen, really I can just do what I did the last time, but I'm going to type it in again so everybody's with me. You're doing the derivative of s, so we're going to differentiate y1 of x, comma x, and close our parentheses. And then we want to plug in 15. So we're going to do such that x equals 15. And that is going to give us negative 5.52669. So we would need to write down S prime of 15 equals negative 5 point, I'm going to just do 527. Round it to 3 decimal places, or you can keep the whole decimal if you'd rather. So for this problem, since it's Calculator Active, you don't have to show where you plug the number in. Just writing S prime of 15 is enough to show that you plugged 15 into that derivative. You don't have to show what the derivative is. You just have to find this value. And if we think about our graph of S, on our x-axis, our x is our days. Tells us right here, x is days. And then the weight of the storage container in tons here. So if we're looking at the derivative, we are taking the change in y over change in x, the slope of this graph, which will be tons per day. And so since we are plugging in 15, that would mean on day 15. So on day 15, this function measures the weight of the sand. So the weight of the sand in the storage container is it's going to be decreasing at a rate of 5.527 tons per day. And you do not want to use a negative here because the word decreasing takes care of the fact that that is negative. If you say something's decreasing at a negative rate, it would actually mean it's increasing, so you do not want to use the negative right here. Okay. Now, this shouldn't have that A right there. For part B, we are asked to find the second derivative at 15. So, to do this in your calculator, you actually can just take what you already had in here and tell it to differentiate it again. So to do that, I think anyway, let's see if this will work. We're taking the derivative of the derivative. So I got the derivative of y1 of x. I have to put a comma x here, close that parentheses, and another comma x, and close that parentheses. I still want to plug in 15, so I'm putting such that x equals 15. Let's see if this works. It does. So we get s double prime of 15 is going to equal 0.276. And let's think about our units a little bit here. All right. And so on our x-axis, we still have just the same thing. We still have days. But on our y-axis, we've got tons per day. So that means our change in y over change in x, the derivative of our s prime, is going to be tons per day over days, or tons per day per day. Or, if you would rather, you can say that's tons per day squared. I kind of prefer doing tons per day because sometimes students put the square in the wrong place here and they say square tons per day, which is not correct. So I usually do tons per day per day. So what we're looking at here with the second derivative is the rate of change of the rate. So we're going to say on day 15, okay, the rate of change of the weight of the sand in the container is, and this time we'll say it's increasing at a rate of 0.276 tons per day per day. Okay, so notice here, whenever we're talking about second derivative, we're talking about the rate that the rate of change is changing. So I've got the rate of change of the weight of sand is increasing at a rate, so you should have double rates there. It's the rate of change of the rate of change. So it's the rate of change of the weight of sand is increasing at a rate of 0.276 tons per day per day. This is like acceleration whenever you're dealing with speed here. So although the amount of sand is decreasing, the rate of change is actually increasing, so it's kind of slowing down that loss. All right, let's look at another one. All right, and so this is going to be sort of like a free response question that we'll be looking at here. I'm actually just going to change the font size. actually, let's see now. Okay. All right, so the depth of water in a rain gauge is given by the twice differentiable function r for 0 less than t less than 24, where r is measured in inches and time is measured in hours. Values of r prime of t, the derivative of r at selected values of time, are shown in the table above, I should say below. It is known that the graph of r is concave down from 0 to 5. So A asks, is there a time from 0 to 24 at which the depth of the water in the rain gauge is changing at a rate of 0.5 inches per hour? And we need to justify our answer here. So if we look at what it's asking for, it says at which the depth of water in the rain gauge is changing at a rate of 0.5 inches per hour. So the rate of change of the water is what we're looking for. So we're looking for a time when r prime of t, our rate of change of the amount of water, equals 0.5. R gives us the amount of water. If we look at our table here, our rate of change of our amount of water goes from 0.3 to 0.2 to 0.03 to 0 up to 0.55, back down to 0.4 to 0.2. So you notice that we are, like right here at 12 hours we're at 0, then we're up at 0.55. So the only way this can happen is if our rate of change goes to 0.5 at some point. So we know this is the case because it tells us r is twice differentiable. So this is actually our intermediate value theorem. If we had values of r, we could do mean value theorem, but we don't have values of r, so we can't do that. So we would say since r of t is twice differentiable, we know that r prime of t is continuous. And so you can pick really any value here below 12, like any number will work for this. I'm just going to use 12. I'm going to say, therefore, intermediate value theorem applies. And since we got, I'm going to do r prime of 12, and r prime of 12 is 0, which is less than or equal to 0.5, which is less than or equal to 0.55, which is our r prime of 15. So since 0.5 falls between those two values, there must be a value C on, actually it only has to be on 12 less than or equal to T less than or equal to 15, because those are the 2 points that we're looking at, such that r prime of C equals 0.5 inches per hour. So the depth of water in the rain gauge is changing at a rate of 0.5 inches per hour for some time on 0 less than or equal to t less than or equal to 24 hours. So kind of restate the question there at the end. Alright, so that would be part A. All of the beginning part is the same here, so I'm not going to reread that. For B, it says use the data in the table to approximate R double prime of 16.5. Show the computations that lead to your answer. Using correct units, explain the meaning of R double prime of 16.5 in the context of the problem. So we are given R prime. To estimate the derivative of that, we're looking at the slope. 16.5 falls right here, halfway between 15 and 18. So we would use these 2 points. We got 15, 0.55, and 18, 0.4 as our 2 points. So we're going to say R double prime of 16.5 is approximately, we're going to use the squiggly equal signs here, and we're just going to do slope formula. So 0.4 minus 0.55 over 18 minus 15. So that's going to be negative 0.15 over 3, which is going to give us negative 0.05. If we think about our units here, it's change in y over change in x. So the y in this case would be inches per hour. And then our x is hours. So when we're talking about a second derivative, we're talking about the rate of change of the rate. R gives us the amount of the height of the water in the rain gauge. So we would say at 16.5 hours, the rate of change of the height of, or depth, does it say depth? Depth, let's use the word depth. The depth of the water in the rain gauge is changing, or let's say decreasing because it's negative. The second derivative is negative, decreasing at a rate of 0.05 inches per hour. So the rate of change of the depth of water is changing at a rate. So it's the rate of the rate here whenever we're talking about R double prime. Okay, I'm going to skip C because we have not done this line approximation stuff yet. So we're going to get to that in this unit, but I'm not going to do this problem. And we're going to skip to this last one. So we've got this equation. It models the percentage of students who pass the 8th grade math exam in North Carolina from 0 to 50, where T represents the number of years since 1980. We want to find E prime of 15 and interpret its meaning in using correct units. This would be one that would be calculator active. So we'll go over to our calculator and let's type in this function. So we got 0.5 times e to the 2 times, now this is tough to type in here, because when we got sine squared of 0.1t, that is like having 2 sine of 0.1t squared, and that's how we have to type it into the calculator. So we're going to put some parentheses here. We'll do sine of 0.1, we'll use an x. We're going to close that parentheses for sine, then close that extra parentheses around the sine and raise it to the second power there. And then we need to close our parentheses for our exponent so that our plus x over here is no longer in the exponent. And then we have a plus 50 on the end. And let's hope I did that right. I think that looks good. The calculator won't put that square right here for us like we'd like to see it, but I think everything looks good there. So if we want to find the derivative, since I've got that in y1, I want to just take the derivative of y1 of x, comma x, close my parentheses. I don't care about actually writing down what it is. They only ask me for e prime of 15. So I'm just going to go ahead and do such that x equals 15. And I get 0.603 here. So I'm going to say e prime of 15 is approximately, actually no, we don't have to do approximately here, 0.603. I guess it's okay to do approximately because we did round a little bit here, but equal sign will be fine in this particular case. So we got to think about what this means. And so if we think about E of t, it tells us the percentage of students who passed. So passing percentage goes on our y-axis. And t is our years, specifically our years since 1980. So when we have t equals 15, it's 15 years after 1980. So that would be in 1995, and we're going to say the percentage of students who passed the 8th grade math exam in North Carolina. And since we've got a positive number for our derivative, we're going to say was increasing at a rate of 0.603 percentage points per year. So we would see that percentage increasing there. So that is everything that we have for the notes. You are going to have a worksheet that you're going to do on your own. I'll have the answer key posted for that so you can kind of check as you're going how you're doing for that. And we will go over this more tomorrow if we need to. I know doing notes online without me there is not ideal, so I'll give you guys time to ask questions if you have any.